Example: an Alaskan rescue plane drops a package of emergency rations to stranded hikers, as shown in the figure. The plane is traveling horizontally at 40 meters per second. So the original velocity for the plane is 40 meters per second, and it is horizontal along the x-axis. It was flying at a height of 100 meters above the ground. 100 meters above the ground. Neglect a resistance. A, where does the package strike the ground relative to the point at which it was released? B, what are the horizontal and vertical components of the velocity of the package just before it hits the ground? C, what is the angle of the impact? This is a nice example that I selected for discussion. So here, for y, we know it is equal to v naught yt minus half gt squared. V naught y is 0. This is one thing that I want you to learn. Wherever you see the word it drops or dropped, whether it is present or past, this is another way of saying the initial velocity along y is 0. Okay? So when you drop the package, this means the y, the original value for the y velocity is 0. So here the initial value for the velocity along y is 0, so the first term vanishes. We end up with just this term, minus half gt squared. G is 9.8, half of that is 4.9, multiplied by t squared. We know that y is minus 100, so now we can solve this equation for the time. T equals 100 divided by 4.9 and square root of that, which is 4.52 seconds. The beauty of this physics problem, although x and y motion are independent, but they both share the same time. They both share the same time. As the y was going down, the x was increasing in this direction. So the same time which we obtained from the first part, the same time is the time needed for the horizontal travel. So now for x, it's equal to v naught xt. V naught x is 40 meters per second. All what we need to do, just multiply that by the time, 4.52. The answer, 181 meters. So this distance is 181 meters. Very simple. Okay. Now, to find the angle of the impact, you need Vx, you need Vy. Vx is V naught cosine theta cosine 0, which is 40 meters per second. And Vy here is V naught sine theta minus gt. V naught y is 0, so it is just minus gt, minus 9.8 multiplied by 4.52, so it is minus 44.3. So now tan theta Vy divided by Vx, Vy divided by Vx, tan theta is minus 1.11, and theta is arctan minus 1.11, which is minus 48 degrees. Okay? Nice example. Another example. An athlete participates in a long jump competition, leaping into the air with a velocity v naught at an angle theta naught. That is the horizontal velocity, the original velocity. Obtain an expression for the length of the jump in terms of v naught, theta naught, and g. So again, we make use of what we discussed, what we learned. At maximum height, the velocity in the vertical direction is 0. So if you use this kinematic equations, V final equals V initial plus AT, V final is 0 equals V initial minus GT. So from here you can solve for T. T equals V naught Y divided by G, and V naught Y is V naught sine theta. Okay. This is half the trajectory. Maximum height here means half the trajectory. So the time needed to reach maximum height is T. The time needed for the full path is 2T. 2T. So the total time, 2T, is 2V naught sine theta over G. Now we are ready to solve. Delta X is the time multiplied by the velocity. The time is 2V naught sine theta divided by G. Multiply that by V naught X, which is V naught cosine theta. So this is the final answer, because we were asked to find the answer in terms of V naught, theta naught, and G. This is the answer in terms of V naught, theta naught, and G. We call this the range for this jump. Check your understanding. Suppose you are carrying a ball and running at constant speed, and wish to throw the ball and catch it as it comes back down. You should do one of the following. Throw the ball at an angle of about 45 degrees above the horizontal and maintain the same speed. Or throw the ball straight up in the air and slow down to catch it. Or throw the ball straight up in the air and maintain the same speed. Which one would you choose? Remember the sailor and the mast? This is a similar problem.
Would it be one?
I am afraid this will not help. If you throw it at 45 degrees, then you will not be able to catch it.
Right. Because it catches
Is
like
it number 3?
more distance.
Number 3. I told you it is very similar to the sailor and the mast and the wrench problem. Okay? So if you throw it straight up, you are not changing the horizontal velocity for you or for the ball. Both of you will maintain the same original horizontal velocity. So it will go up, then it will return back to you. Does that make sense? The important thing, the trick here is that neither you nor the ball are gaining or losing any acceleration in the horizontal direction. You are keeping the same original value. It's just the ball went on a short round trip up and then returned back to your hands. Okay? So this is the answer. Another one. As a projectile moves in its parabolic path, the velocity and acceleration vectors are perpendicular to each other. Everywhere along the projectile path, at the peak of its path, nowhere along its path, not enough information. Think for a minute and give me your answer. Any suggestion?
2.
Yes, thank you. 2 is the right answer. Because 2 at the peak of the path, as you can see here, the acceleration is downward and the velocity, only the horizontal velocity is there because the vertical velocity is 0. So at the peak, at the maximum height, the velocity is all horizontal, the acceleration is all vertical, they are perpendicular to each other. At any other position, there is another angle between them. Okay, thank you. The strategy that we need to apply when we solve problems, usually it is good to sketch the problem. Then you need to decompose the original velocity into x and y components. You need to treat the horizontal and vertical motion as independent, but they share the same time. This is very useful piece of information. Then take in mind that horizontal motion is without acceleration, ax is 0, velocity will always be the same. The vertical motion, it has constant acceleration, 9.8 meter per second squared, directed downward always.